Just can't get enough of those triple integrals, hey? Well, welcome back. We're going to do definition 6.2.2 and example 6.2.2. Definition 6.2.2 is about the average value of a function f of xy over a solid S. And so f average is 1 over the volume of S, which we saw in the previous video, times the triple integral over S of the function f of x, y, z dv. Example 6.2.3 says, let S be the part of the first octant bounded by the planes 3x plus 2z equals 6 and 3y plus 4z equals 12, as in the previous video. So we have that already set up. We're just going to borrow the result that we have there. So there is the volume that we need to calculate, set up over that solid S in as a type 2 solid. So we're asked to suppose that T of xyz equals x gives the temperature at every point x, y, z in space, and I'm asked to find the average temperature over S. So we're going to apply this formula, which means that we have two triple integrals to evaluate, one for the volume and one for our function t. So let's get started. We're going to take our volume integral here. So the volume of S is the integral from 0 to 4, the integral from 0 to 3 minus 3/4 y, the integral from 0 to 2 minus 2/3 z of 1 dx dz dy. So let's go and evaluate this. If we differentiate dz, so we are getting not dz, dx, we're getting x that we need to run from 0 to 2 minus 2/3 z, and the remaining integrals stay the same. So from 0 to 4, the integral was dz dy, not dz, dz dy, and running the fundamental theorem, subtracting 0 at the bottom gives us, so honestly, one of the longest parts of evaluating triple integrals is just recopying the integrals. We have here 2 minus 2/3 z, which we're going to integrate with respect to z, and then again with respect to y. So antiderivative that we need here is going to be 2z minus 1/3 z squared. And we're going to take this from 0 to 3 minus 3/4 y. This is in the integral from 0 to 4 of this monster dy. So again, we have a 0 on the bottom, so that will give us 0 in both of these terms. We just need to plug in the top, so we're going to have the integral from 0 to 4 of 2 times 3 minus 3/4 y minus 1/3 of 3 minus 3/4 y quantity squared dy. Now this algebra is something I'm sure that you can do. We're not going to waste any time doing it here. I've done it on the side. This is going to reduce to 3 minus 3/16 y squared dy, which again I need to anti-differentiate. So 3y minus 1/16 y cubed, which is going to go from 0 to 4. 3 times 4 is 12 minus 64 over 16 minus 0 again. 64 over 16 is 4. 12 minus 4 is 8. 8 cubic units. That's a volume after all. So there is our volume. Now we need to do the same thing for our temperature T, except it's not going to be a 1. So I'm not going to bore you with those details. You have seen a triple integral at least once here. You know how it is going to be set up. But if we take T of x is equal to x, so we are going to do that integral from 0, the same thing, 0 to 3 minus 3/4 y, 0 to 2 minus 2/3 z, now of x, dx, dz, dy. Again, you can figure that out. I've done it on the side, and that gives me 6. And so what I'm looking for is T average over S, and that is 1 over the volume, right? Using that formula, it's 1 over the volume of S times the triple integral over S of T of x, y, z, dv. So that is 1 over 8. This integral gave us 6. So 1 over 8 times 6, 6 over 8, 3/4 units of temperature, whatever they are. And so there you have a average value, right, which involves two integrals, one to find the volume, one to find the function over the solid, and then you just divide the two. In the next video, we are going to practice rearranging the bounds of a triple integral when one order is given.